Planet Earth is astonishingly well suited to supporting life. It is large enough to maintain an atmosphere, which in turn means that it can support liquid water on its surface. And thanks to that atmosphere, global temperatures have never exceeded 60 degrees Celsius, nor have they ever fallen below minus 90 degrees Celsius. The annual average is a comfy 15 degrees Celsius. Fortunately, the Earth has managed to hang on to that atmosphere for over 3.8 billion years, thanks to its swirling molten iron core. That turns it into one huge magnet, generating a massive magnetic field that extends far out into space. Without that magnetic field, the Earth's atmosphere would have been stripped away long ago. That, in turn, would have meant that the surface of the Earth would have been exposed to the full force of the sun's blistering ultraviolet radiation and a constant stream of charged particles known as the solar wind. The emergence of life, as we know it, would have been impossible. But our little sister Moon enjoys none of the benefits of Earth. It has no atmosphere, it has almost no magnetic field, and it's tiny. In short, the Moon is about as inhospitable as it's possible to be. On the Moon, the sky is always jet black, both by day and by night. The lunar surface is subject to dramatic extremes of temperature. By day, the temperature in direct sunlight can reach over 120 degrees Celsius. By night, the temperature can drop to a distinctly frosty minus 153 Celsius. Even the concepts of day and night are different on the Moon. A lunar day and a lunar night are both a little over 14.5 Earth days long, and for reasons that have to do with the interaction of the Earth's and the Moon's uneven gravity fields, that is almost the same length of time that it takes for the Moon to orbit the Earth. They are locked together, which is why we only ever see this, the near side of the Moon, and we never see the far side. This was important when planning the Apollo missions.
The reason why Apollo missions were so short was because they landed in the sunlight and they took off while the sun was still there. Should they have stayed past 14 days into the nighttime, the temperatures plummet drastically. On Earth, the air around us allows us to cool machinery, whereas in space you don't have that. So now I'm designing hardware that may have to operate under conditions that would make the Arctic look like a summer day, and then turn it around and have that maybe operate in the sunlight where you're now at 100 degrees Fahrenheit during lunar daytime.
But the Earth's atmosphere doesn't just help to regulate temperatures at ground level. It also protects us from the estimated 200 tons of interplanetary dust and rocks that plow into its upper layers every day. Fortunately, most of these objects are very small, and because of their extremely high speed, they burn up in the atmosphere long before they reach the ground. It's a very different story on the Moon. With no atmosphere to slow them down, meteorites of all shapes and sizes are smashing into the lunar surface every day, and have been doing so for 4.5 billion years. The scars of these impacts are plain to see in any image of the Moon's face, but look more closely and the reality becomes even more worrying.
Imagine taking a glass and smashing it. You don't get nice rounded pieces. You get these shards with very jagged edges. And that's what the soil or lunar regolith is like on the Moon. It's extremely abrasive. Also, it's been pummeled for millions of years through asteroids and such. So these small abrasive particles can get into spacesuits and to moving machinery and such and cause a lot of damage. There's been anecdotal stories about the Apollo astronauts' suits, the joints being highly abraded, such that if the Apollo missions had actually gone more than 3 days, that it might have been very difficult for the suits to survive in that environment.
Mechanically, it's very difficult to deal with. It's very abrasive. It's all broken up in small angular pieces. The glass is very sharp. They have sharp little edges, and that can cause moving parts to stop. You can get silicosis of the lungs. There's all kinds of problems you could have with that.
Currently, one solution to the problem is to never let the dust get inside the living quarters or the vehicles. On this lunar rover, the spacesuits are fixed to the shell of the cabin in such a way that the astronaut enters and exits their suit from the rear. The backpack is, in effect, also the access hatch into and out of the interior. The suit, and more importantly, the dust on it, never enters the cabin. But not all of the hazards of lunar living can be mitigated as simply. The lack of an atmosphere, combined with the moon's almost non-existent magnetic field, means that the lunar surface is also bombarded with high-energy particles coming from all directions. It's called cosmic background radiation.
Now, these come from deep space. You can't stop them. They're going to penetrate almost anything. Right now, the only way to deal with them is to accept that hit and hope that you don't get a really bad hit from one. A more difficult problem, but one that you can deal with, are solar particle events. These are the coronal mass ejections, CMEs, where you have the sun throws out huge quantities of highly energetic charged particles that travel through space and will kill you. Effectively, they're extremely high radiation.
The Earth's magnetic field and atmosphere shield humans from that. But in space, that's not there. So this radiation from both our own sun as well as this cosmic background radiation are significantly challenging aspects of designing hardware.
But there's one potential health hazard that can never be overcome. Compared to Earth, the moon is tiny. Its diameter is only 27% of Earth's. It would fit neatly into the North Atlantic basin, and its mass is just a little over 1% of Earth's. All of which leads to the fact that the pull of gravity on the moon is just under 17% of the gravity on Earth, about a sixth. To date, 12 humans, all of them Apollo astronauts, have spent an accumulated total of just 80 hours on the moon's surface. Long enough to collect some rocks, drive around a bit in the world's most expensive car, and plant a few flags. But not long enough to assess the biological consequences of living and working in 1/6 G. It's already clear that microgravity, or zero G, takes a heavy toll on even short-term visitors to the space station. From bone loss to impaired vision, from red blood cell loss to cardiovascular changes, from fluid redistribution to changes in coordination. These are just a few of the physiological degradations that astronauts have to endure and try to counteract.
We know that there are physiological deterioration in microgravity, and they have to adopt countermeasures for that. What we don't know is how the human body responds to long periods of time in 1/6 gravity of the moon, and that's a big question.
It may turn out to be the biggest.
The imagination of science fiction writers, and a lot of people in my business cut their teeth on science fiction. So they read science fiction, they watched science fiction movies and television as kids. Now they're adults, they're working in the business they always wanted to, and to them, it's obvious you go to Mars. Mars is the planet that's most Earth-like of all the rocky planets, in the sense that it has a reasonably equitable climate. It has evidence for past internal heat. It has evidence for the presence of water in a variety of states. So of all the planets, it is the one most likely to have originated life. And people want to know if that's true or not. So that drive, that question, has sent a lot of people off the deep end of saying, well, Mars is the obvious target, it's the next target, we've been to the moon, we've done that. And I think that's looking at it the wrong way. I don't deny that the origin of life is an important scientific question, but there are a lot of important scientific questions, and that's one of many. And the reason I advocate lunar return is that if you build my system, you can go everywhere. See, I don't just want the moon, and I just don't want Mars, and I just don't want asteroids. I want all of that. And the way to get all of that is to build a system that's robust, that's incremental, that allows you to gradually but continuously extend your reach.
I don't necessarily look at moon versus Mars. I basically look at, what's the logical progression to get to Mars? Can I use the lunar surface as a proving ground before I go to Mars? Now, the environments are obviously different. Mars has an atmosphere, even if it's tenuous. Its seasonal variations are different than the moon, but there's enough things that you can do on the moon that could help you get to Mars. What's going on now is a lot of countries are looking at Mars as being, a bridge too far at the moment. That's fine. And therefore, the moon makes a lot more sense. It's relatively close. The United States has been to the moon, so to a certain extent, it's not a been there, done that, but it's we know we can do it again. There are countries that are just literally getting outside of Earth orbit for the first time. So going straight to Mars really doesn't make a lot of sense for those countries.
The people in China and people in India and Japan, they want to see people on the moon from their country in their lifetimes. They want to do it. They don't want to sit around and talk about it. They want to do it. And so I think that's why there's intense international interest in the moon. It's a goal that's achievable. It's a goal that has value in terms of creating spaceflight capability. And it's something that excites a lot of their supporting public. So they're very interested in the moon.
To many in the Moon First community, the practical benefits of being able to test a new generation of off-world technologies are very appealing. Not least because if anything goes wrong, help is only days away rather than months or even years. But that's not the only reason to return to the moon.
The second thing, though, is the moon on its own has tremendous resources and a reason for being there besides just science. And so whether it's the minerals and the types of different metals that may exist on the moon, whether it's water, those are things that society can use. So in 30 or 40 years, hopefully we've started to not just go to the moon and look at the rocks and set up telescopes and things like that, but we're actually trying to use it commercially.
And on the face of it, the commercial value of the moon could be literally out of this world. Distilling rocket fuel out of moon rock could be extremely profitable, as could mining platinum metals and rare earths. And the rare isotope helium-3 could turn out to be priceless. It may be the most valuable substance known to humankind, and unlike the Earth, the moon has millions of tons of the stuff distributed across its smiling face. The list of lunar goodies just keeps growing.
This has obvious commercial value. And in fact, it will never be done as a government program. It's always going to have to be, there's going to have to be some commercial value and some group of investors and operators to make this thing work on a long-term basis. Now, my feeling is that the best way to induce commercial activity on the moon is to have NASA lead and show that it's possible, to show how difficult it is and what it costs, and then have the private sector take that over and innovate.
In the last few years, over a dozen companies have begun to make their spacefaring intentions public. Some are offering economical trips to low Earth orbit. Others are offering innovative space habitat solutions. Yet others are promising to cash in on the resources to be found on the moon and on asteroids. In each case, the plan is to hasten slowly, to take small steps that can build upon the one before.
Remember, we didn't first land the lunar module on the moon. We first landed a small little thing called Surveyor, and we actually crashed a few things called Ranger before that. So we started small to learn how to do it, to show that it could be done. And that's sort of the approach being taken by the small companies like Moon Express and Astrobotic and the Israelis, who are all competing for the Google X Prize. And that's the first step. That's the way to sort of let people get their feet wet with the concepts of designing spacecraft, delivering small payloads, that's one way to develop a commercial industry, is to seed it with a prize and let people compete for it.
The Google Lunar X Prize challenges privately funded spaceflight teams to land a robotic spacecraft on the moon, travel 500 meters, and then send back high-definition video and images of the terrain. The winning team will net a cool $20 million. But the bigger goal is to incentivize entrepreneurs to create a new era of affordable access to the moon and beyond, and to inspire the next generation of scientists, engineers, and explorers. Many observers believe that the next boot print on the moon will be Chinese, closely followed by those from the host of other nations who dream of becoming spacefarers. They too will proudly plant their national flags in the moon's unforgiving regolith. Interestingly, some say symbolically, when they get around to looking for the 6 American flags planted by the Apollo astronauts, they may be surprised by what they find.
Those flags have been on the moon now for almost 50 years, and they've been exposed to the full fury of 14 days of lunar sunlight, where the sun is searing their surface, and it gets up to the surface temperature is 100 centigrade at noon, and the numbing cold of lunar night, which follows 14 days later, and it gets down to minus 150 C. And if you look at any flag that's been out on Earth for a long period of time, you'll notice that the colors are faded. I suspect that the flags on the moon are largely white because they've been bleached by solar ultraviolet for 50 years. In a way, that's kind of symbolic. We've got 6 flags planted by Americans on the moon. All of them are now white.
That symbolism reflects the essence of the United Nations Outer Space Treaty, which clearly states that the exploration and use of outer space, including the moon, is the province of all mankind. Time will tell whether that treaty will hold as a new era in space exploration and development dawns. But what is certain is that our moon and our solar system are about to be changed forever.
I was strolling on the moon one day in the merry, merry month of December. Now, May, when much to my surprise, a pair of bunny eyes.
Jack Schmidt's career as a singer was never destined to go very far, but his career as a geologist took him further than any scientist before him. Schmidt was the first, and still is the only scientist to set foot on the moon. During their extensive moonwalks in December 1972, Jack Schmidt and Gene Cernan collected a treasure trove of rock samples that would keep geologists back on Earth busy for years. But the answer to one question eluded them. Would they find evidence of water in the lunar dust? Because if they did, we could split it into its component elements to make the most powerful rocket fuel known to man. And our moon would become an invaluable gas station in the sky for future spacefarers. In the late 1950s and early 1960s, orbiters and landers from both the United States and the Soviet Union became regular visitors to the moon, surveying the surface and sampling the lunar landscape. From 1969 to 1972, the Apollo program managed to place 12 humans on the moon and bring them back alive. Together, they returned to Earth with a total of 382 kilograms. That's almost half a ton of moon rock. But even given all this activity, most of the surface of the moon remained unexplored. And what was learned from those brief forays across the magnificent desolation of the moon was limited.
We've landed in 6 spots. All those 6 spots were within 25 degrees of the equator. And we learned quite a bit about the moon. We learned what its basic chemical composition is. We learned how it works, what geological processes have shaped it, what its history is, what its evolution has been over the past 4.5 billion years. So we have a pretty good understanding of that. And we made a rather startling discovery in the last 20 years that we don't know everything that we thought we did, that the poles are a unique environment. And the reason they're unique is because of the way the moon's spin axis is oriented.
The Earth's axis of rotation is significantly tilted in relation to the plane of its orbit around the Sun, a full 23.4 degrees. That's what gives us our seasons, and it's why, when it's summer in the northern hemisphere, it's winter in the south. But the moon's axis of rotation is hardly tilted at all with respect to its plane around the Sun, a skimpy 1.5 degrees. And that creates some rather unique conditions at the moon's poles.
What that means is if I'm an observer standing at the pole, I always see the sun at or near the horizon. Now, if I'm on a peak, I will actually stick up into the sunlight. I'll see the sun all the time. But conversely, if I'm in a hole, I'll never see the sun. So that simple relation of the spin axis and the sun is responsible for creating a unique environment at the poles. The areas that are in permanent darkness are extremely cold. If any kind of water molecule gets into them, it can never get out again. There's no known process to remove it. Now, the moon is bombarded by water-bearing objects and has been for its entire history. There's water in cometary cores, there's water in meteorite minerals, there's water in interplanetary dust. So those water and hydrogen-bearing species hit the moon constantly, and most of that's lost to space. But the stuff that hits the moon and finds its way into a cold trap is trapped. That's why they're called cold traps. And so the thought was, well, maybe there's an appreciable amount of water ice in these craters. And we didn't really know. And all the Apollo missions were sent in equatorial orbit, so we didn't have the instruments needed to look into those dark areas and see what was there. So it wasn't until 20 years after Apollo in 1994, the Clementine mission orbited the moon for 71 days and mapped the moon globally. And we improvised an experiment with Clementine to use radio waves to bounce them off the floors of the dark craters and look for ice. And we finally concluded that we did see evidence for ice reflection in the radio waves sent by Clementine. Now that set off a 20-year set of missions from a variety of countries. There was a Lunar Prospector mission that NASA sent in 1998. There was the SMART 1 mission in the early 2000s sent by the European Space Agency. The Japanese sent a Kaguya lunar orbiter. The Chinese have had 2 lunar orbiters. India sent an orbiter, Chandrayaan-1, and the Americans sent the Lunar Reconnaissance Orbiter. All of them carried a variety of instruments using different techniques to look and map the dark areas of the moon. All of them found evidence for substantial quantities of water there. We finally proved it, without a doubt, through the impact of something called the L-Cross. And it was the upper stage of a rocket that was slammed into the moon, and then we looked at the ejecta thrown out by the impact of that rocket. And what we found was that water vapor and water ice particles were thrown out by that impact. The amount of water turned out to be between 5 and 10% of the total amount of ejecta. Doesn't sound like a lot, but that actually is quite a bit, considering that most people thought the moon had virtually no water at all. So we know that there's water there. What we don't know is what its detailed properties are, and that's what we need to find out before we go back.
The presence of plentiful, accessible water on the moon may be the single most important unanswered question underpinning any decision to return. Such major questions, and there are many in the realm of space science, are known as strategic knowledge gaps.
There are 2 aspects to understanding the SKGs, the strategic knowledge gaps. You want to know how the ice is distributed and what its configuration is and its physical properties, because you want to know where it came from. You want to know its origin, you want to know its evolution, you want to know the geologic scientific story behind the water. The other aspect of it is the utilitarian value of it. I want to harvest that water. I want to use that water for a variety of different useful products. But before I can do that, I need to know where it is. I need to know what its physical state is. I need to know how to get to it. And I need to devise a technique that allows me to extract it from where it is. So the strategic knowledge gaps reflect our ignorance. They reflect the amount of things that we don't know about the ice that we need to know before we can actually start using it for practical purposes.
The answer, many believe, is to dispatch a robotic rover to the moon's south pole, with instructions to get out there and start digging. It's a mission known as the Resource Prospector.
Resource Prospector is a mission that NASA has been looking at for the last several years, which is to send a rover with a drill and an oven and some instruments that will help search for water. And it will drive hopefully something on the order of 1 to 3 kilometers, taking, several drilling sites along the way. And that will give us a first taste. It's that geologist with his hand lens looking, okay, is this a region of interest? It's like mining on Earth. Step 1 is prospecting. You take aerial photos, you look at pictures from satellites, and you look for regions of interest. And you say, hey, that looks really interesting. I'm going to go send a prospector there. And that person's going to go and he's going to pick up rocks and take samples. So step 1 really is doing that. And then from that point, we'll hopefully be able to set up some kind of a mining operation. Here again, starting out small. We're not going to churn out commercial quantities of these things. We have to test our techniques, verify all the operations, let it run for a period of time, see if it breaks. If it breaks, I've learned something. What kind of maintenance do I need? From that, I can build a business case. Okay, I now know where the resource is. I know how difficult or how easy it is to extract. I've demonstrated these things. Now can I scale it up? And so over time, that's kind of what I hope to see, is we do this first step, prospecting.
So Resource Prospector I consider to be a first step, not an end step, in what we need to learn about.
If the scientists, engineers, and entrepreneurs are to be believed, space will soon be buzzing with a new breed of spaceships, piloted by a new generation of astronauts. And many of these space scientists believe that our nearest planetary neighbor, the Moon, will play a key role in these new initiatives. To them, our Moon offers everything that the next phase in the development of space is going to need. And the good news is that, in astronomical terms, it's right in our own backyard.
In a way, we're really lucky because we have this object orbiting the Earth that's so close that we can get to. You can go to the Moon anytime you want. There's a launch window open 24/7. It only takes 3 days to get there, and it has the materials that you need to create space flight capability, and it has them in the form you need them in. It will allow us to build a system to let us go anywhere. And I think that's really the ultimate goal of spacefaring. You want the ability to go wherever you want to go with whatever capability you need to do whatever job you can imagine for as long as you want to. That's the real object of spaceflight.
It's been over 4 decades since the last human boot print was planted in the lunar dust. The date was December 1972, and the boot belonged to astronaut Gene Cernan as he prepared to join his colleague, geologist Jack Schmitt, on board the lunar module of Apollo 17 and head for home. He had these carefully scripted words to say as he mounted the access ladder.
And as I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just let what I believe history will record that American challenge of today has forged man's destiny of tomorrow. And as we leave the moon in Taurus Littrow, we leave as we came, and God willing, as we shall return with peace and in hope for all mankind. Godspeed the crew of Apollo 17.
Everyone in NASA and the space community knew that this would be the last Apollo mission, and that new ventures such as Skylab, the shuttle, and the space station were on the horizon. But like Gene Cernan, most people also thought that a manned return to the moon would not be long in coming. Few would have believed then that mankind's return would be over half a century away in the 2020s. From its first flight in 1981, the Space Shuttle transformed manned spaceflight and enabled many new missions to be conducted in low Earth orbit, about 400 kilometers or 250 miles above the Earth's surface. Low Earth orbit, also known as LEO, is where the shuttle hosted 22 Spacelab missions, launched the Hubble telescope, and played an essential role in constructing the International Space Station. In 2011, the last shuttle, Atlantis, delivered a key module to the ISS and returned to Earth just before dawn on July 21st.
Landing gear down and
It was the end of an era of supreme achievements by what had been originally conceived as a reusable, cost-effective space truck.
Shuttle originally was named STS, and it was called Space Transportation System. And the idea was that the shuttle, the actual shuttle that we know and love, was the first piece of a space transportation system. It was never intended to be the ultimate end piece. It's the first piece because it can transport people and cargo from the Earth's surface to LEO. And then from there on, you would have another vehicle that would transport them to these other localities. If we had kept with the original idea of having an incremental system that gradually expands our reach with time, that would have been the next logical step, to build a reusable vehicle that could go back and forth between the station and higher points in Earth orbit.
The problem has been a combination of cost and physics. And until now, the two have been inseparable. The physics problem is simple to state, and it's called gravity. The cost problem is equally simple to state: to defeat, or at least manage, that gravity. All objects that have mass distort the space around them and are attracted to each other as a result. And the larger the object, the greater the distortion, and the greater the attraction. It's a fundamental law of nature. And for a rocket scientist, overcoming and managing gravity poses some of the most difficult design challenges of them all. It directly affects the ease with which it is possible to move around in space, because it determines the energy that needs to be spent to travel from one place to another, or to escape the gravitational field of a planet or a moon. That gravitational field is often referred to as a gravity well.
The more mass a planet or an object has, the harder it is to escape from its pull. So the bigger planets have very deep gravity wells. As you go down the scale in size, the escape and orbital velocities become correspondingly smaller. Finally, you come down to an object that's small like the Moon, which has 1/6 the gravity and 1% of the mass of the Earth, and its escape velocity is much smaller than the Earth's.
Which is a crucially important fact when you're trying to build a moon-based space transportation system. The Earth's gravity well is the deepest in the inner solar system, a fact which leads to some startling statistics. Over 85% of the weight of every rocket launched from the Earth's surface is the weight of the fuel required to lift itself out of our gravity well, at an eye-popping $20,000 per kilogram. For the shuttle, this meant that at launch, the combined weight of the solid fuel boosters the external fuel tank, and the orbiter, was typically 2,000 metric tons, of which only 100 metric tons was the orbiter and its payload. This simple imbalance between fuel and payload is the reason why lofting a single kilogram of mass into orbit has traditionally been so expensive.
There's two kinds of mass that you launch. There's smart mass and there's dumb mass. Smart mass are things that have high information density, like a computer. But dumb mass is a ton of water or a ton of liquid hydrogen. The rocket doesn't care. It has to lift it up against the gravity field of the Earth. What we're trying to do is to move to a template where we're getting most of the dumb mass from sources other than the Earth.
And at the top of the dumb mass shopping list for space engineers is propellant, rocket fuel. And this is where the moon enters the picture. If it were possible to generate liquid oxygen and liquid hydrogen, the two most powerful rocket fuels known to science, on the moon, then here would be a source of propellant that would be conveniently sitting at the bottom of a very weak, very shallow gravity well at the heart of the Earth-Moon transportation system. Homegrown, locally available, and cheap, all powered by the moon's water. Intriguingly, this would also enable future space engineers to take advantage of a theory first proposed in late 18th century France by astronomer and mathematician Joseph-Louis Lagrange, who suggested that there could be a few rather unique gravitational locations in the space between suns, their planets, and their moons.
Whenever you have two gravitational bodies, there are places around those where the gravity kind of cancels out the effect of each other.
These points are effectively the neutral buoyancy points of, they call them weak stability boundaries, but they're places in the Earth-Moon system that are easy to get to other places from, and that's why they're of strategic importance.
So depending on these locations, you can potentially set up a space station or a depot or whatever the case may be, and it will stay in space at that location with very minimal amounts of propellant to keep it there.
When you factor in propellant manufacturing on the moon and the strategic use of the Lagrange points, the space transportation system starts to look much more feasible and affordable. And that, the space scientists suggest, is going to require a family of transport vehicles, each specifically tailored to their individual missions.
Do you want something that goes from the Earth's surface to the moon's surface and back again? The answer is no. You're going to break that up into chunks. Okay, I want something that goes from the Earth's surface to maybe some orbit around Earth, whether it's low Earth orbit or geosynchronous or whatever the case may be. Now I'm going to want to have something that goes from Earth's orbit towards the moon. Do I want to go all the way to the moon, like we did in Apollo and break, or do I want to go to a midpoint, such as a Lagrange point, and then have that transportation system just go from Earth orbit to the Lagrange point and back, and then have another transportation go from the Lagrange point down to low lunar orbit or to the lunar surface. So you're kind of breaking up your system. So at that Lagrange point, if I take this approach where it is now the hub of my two transportation systems or railroads, well, I'm going to probably want to put a fuel depot there. My gas station. I'm not taking everything with me to come home. I'm only taking half of what I need, which makes my launch vehicle and transportation system smaller.
Part of this new multi-part transportation system is likely to see the introduction of a wholly new propulsion technology. It's a form of ion drive, known as solar electric propulsion.
You take an element or a molecule and you accelerate it using magnetic fields and electrical fields. Here, you can get extremely high velocities of these particles, but you don't really throw a lot of these particles at the same time. So you have two ways of going to the moon now. With chemical propulsion, it's a fast trip, maybe not as efficient, so you probably would use that for your crew. For cargo, you'll probably want to take this slow approach, high efficiency, where the amount of propellant that you use is not that great, but it may take months to a year to transfer something from Earth orbit to the moon. You have this balancing act, and maybe you might combine the two. Maybe you use chemical propulsion to get you out, mostly out of the gravity well of Earth, and then you use electric propulsion to move around the vicinity of the moon. To go to the moon's surface, here again, you'll need chemical propulsion because of the high thrust you need coming down and getting off the planetary surface. So you'll probably have a combination of these types of transportation systems.
Development is expected to be a long one, measured in many decades rather than a few years. And in the moon business, every step of the way will follow a detailed plan known as the Lunar Exploration Roadmap. From its inception, the roadmap was designed to be incremental, cumulative, and affordable.
So what we decided was the way to do this is to take advantage of one of the biggest attributes of the moon, and that is that the moon is close. It's only 250,000 miles away, 400,000 kilometers. Round-trip radio time is 3 seconds. So if I execute a command for a machine on the moon, I'll see the reaction to that 3 seconds after I give the command. That's almost near real time. So our big idea is to send a swarm of different robots, all with different functions, to the poles of the moon, and let them begin the task of preparing the moon for habitation and to start mining the water ice. So the first missions go and prospect the moon. I want to know where the highest grade water deposits are. I want to know where the near permanent sunlight regions are. Those are the zones where I'm going to set up my equipment. Those are the zones where I'm going to put down my outpost. Each robot will be operated by an operator on the Earth. They'll be teleoperated. They won't be autonomous. These operators will steer the machines, they'll lead them into the areas where they're going to work, and they will supervise the work through remote control. So over time, we build up more and more of these robotic assets. In our architecture, we plan to send 2 missions per year. So we're landing 2 robotic assets at the poles every year. By the time we get to year 8, we have largely have a completely up and running system that's harvesting water, probably at a rate of about 100 metric tons per year. It's not very much, but that's enough to make the fuel that would allow you to go to and from the lunar surface with a lander. Every year we're adding assets. Every year we're increasing the amount of water we produce. At one point we send the habitat. The robots assemble that. They install it. They put the pieces together. They run power to it. And then finally you're ready to receive people. And I think our first arrival of people comes about 9 years after the robots have started work. They will initially stay for only a few days just to make sure everything's running and plant the flag and pat the robots on the back, tell them to keep up the good work. But eventually our goal is to have rotating crews of 4 that come twice a year and stay for 90 days each.
Dr. Spudis calculates that the break-even point for his plan comes at year 16, when his plant is generating over 150 tons of water, which in turn is being converted to liquid hydrogen and liquid oxygen for rocket fuel. But many international moon watchers suspect that by that time, other outposts will also have been established across the moon. A number of spacefaring nations have made it clear that they intend to plant their own boots on the moon. The Chinese, the Russians, and the Europeans all have well-developed proposals for settling there, all employing their own distinctive approach to habitat construction. One of the most imaginative has been suggested by the European Space Agency. Targeted on the moon's south pole, the plan calls for 2 relatively new technologies to work together: autonomous robotics combined with 3D printing. The habitat is contained within a cylinder, which will be positioned on the lunar surface. Inside the cylinder is an inflatable dome that will form the internal scaffolding of the habitat. 2 robotic printing machines will set to work covering the inflated dome with lunar dust, or regolith. As they work, the 3D printing head will stabilize the regolith with resin, creating a honeycomb of rigid membranes that resemble the internal structure of bone, light but strong. The whole process is expected to take about 3 months, by the end of which time the dome will be covered in 2 meters of bonded regolith, which will protect the inhabitants from meteoroids and radiation, while maintaining a breathable, temperature-controlled atmosphere. The cylinder, which contained the inflatable habitat, now acts as the airlock through which the astronauts can come and go as they please. Eventually, a number of these habitats can be constructed and linked together, creating what has been described as a lunar village. The idea of using lunar regolith to shield and protect habitats from the harsh lunar environment is not new. Engineers and architects created detailed plans in the 1980s to demonstrate the principle. The problem they faced, however, was that the technologies didn't exist to achieve their ambitious plans. Although they did know, thanks to the material brought back by Apollo, that lunar regolith just might turn out to be a rather useful building material.
There were experiments done in the 1980s where people took lunar material and microwaved it. And it actually forms a very nice sintered material, very nice ceramic kind of aggregate. Another person took lunar material and made concrete out of it. He added earth water to lunar soil and actually made concrete. And it held up very well, very fine-grained, very, very good concrete. So there have been experiments with it, but of course no one has built anything with it on the moon. So that's the simplest kind of product you might get from the moon.
But simple homegrown concrete is far from being the only valuable resource on the moon. Surveys have shown that moon dust is rich in platinum, titanium, gold, and rare earth elements, crucial to the semiconductor industry. Initial analysis suggest that many of these products exist in concentrations that would make extracting them from the moon to be at least as profitable as mining them on Earth. But there's one substance that moon dust contains that can't easily be found on Earth. It's thought to be a possible key to fueling future nuclear fusion reactors, and it's a rare isotope of helium known as helium-3. Valued at over $3 billion a ton, it's the most costly substance known to man. Just 100 kilos of helium-3 could power a major city for over a year, which is why multinational corporations, as well as nations, are studying the viability of setting up their own outposts on the moon.
So this has been looked at in some detail, and it's not totally crazy. It can be done. It's estimated that the amount of helium-3 that would fill a shuttle cargo bay, which is about 20 metric tons, would provide the entire energy consumption of the United States for 1 year. So helium-3 is potentially a source of fuel to generate commercial electrical power sometime in the future, after all these engineering problems are solved. But they're not solved yet. So these are some of the things you can imagine coming from the moon. Water is the first thing because it's the easiest and it's initially the most valuable, but a wide variety of other products can be made from the moon as well.
The 2-decade-long lunar exploration roadmap is ambitious, yet practical. Visionary, yet carefully pedestrian. It requires the slow, incremental development of capabilities on the moon, much of it benefiting from evolving 21st century technologies such as semi-autonomous robotics and 3D construction. It also involves a bold view of humanity's place in the cosmos. 2 or 3 decades from now, space may be buzzing with activity.
So what do you have at the end of this time? You have a working outpost on the moon that's largely operated by machines controlled from the Earth. You have permanent transportation elements that are going back and forth. The transfer ship is going from low lunar orbit to low Earth orbit. The other rockets are carrying crews to and from the space station. They're transferring, they're going up to low lunar orbit, they're transferring to the lander, or they're going down to the surface. All of those different activities are supported because I now have a transportation system that can get people and cargo and machines wherever I need them. All this works in theory. It works on paper, but no one's ever done it. No one's ever built a big system from small robotic elements. Nobody's ever extracted water from extraterrestrial materials and then used it in some application. Nobody has ever put together an outpost on a planetary surface using robotic machines controlled from somewhere else. Yeah, it all works in theory, but does it work in practice? And if it does work in practice, what are the pitfalls? What are the problems? What big difficulty have we overlooked? Because there's no doubt in my mind that we have overlooked some difficulty. And that's why you need to have NASA do that, because that's what NASA's in business for. They are in business to do engineering, research, and development. And this is an engineering R&D project. You're going back to the moon, not to mine the moon, but to determine if the moon can be mined.
On July 21st, 2069, it will be exactly 100 years since Neil Armstrong became the first human to set foot on the moon.
It's one small step for man, one giant leap for mankind.
And by 2069, if the lunar exploration roadmap plays out according to plan, mankind will have returned to the moon and will have been developing its potential as a source of water, rocket fuel, metals, rare earth minerals, and helium-3 for over 4 decades. The population on the moon will have grown to include not only astronauts and engineers, but doctors, managers, farmers, and chefs. People will be choosing to live permanently on the moon. A crucial milestone, in Dr. Spudis's opinion.
That's when the lunar outpost becomes a colony, when you have inhabitants that live there by choice forever. Now, at what point might that be? Well, I would think that it would probably be at a point where you've got a significant number of people involved doing a wide variety of different activities, and you are exporting a product that's actually making money. If you have a foothold on the moon, and for example, you're mining water, and you have a company that has the rights to export that and sell that product to various users in cislunar space, then you might decide, well, I'll just stay here to make sure that my operation runs smoothly. Is that a colonist? I would argue that you are, because effectively you decided for reasons that are perfectly understandable that you need to live on the moon. You need to be there to make sure your business operates correctly. So you're a colonist. So the transition from an outpost to a base is just a big outpost. You know, these things are very flexible definitions. But a colony implies permanence. It implies you're going to live there. It implies perhaps your family will live there with you. That may be some time off yet.
And what of the possible pitfalls that Dr. Spudis expects to encounter? Some would argue that the sheer hostility of the moon's environment, combined with its fractional gravity, barely 1/6 of Earth's, are hazards that can't be ignored if people are to survive and thrive on tomorrow's moon.